Okay, well, thanks everyone for tuning in. The first BCGS in 2 years, hybrid format. So we have how many people in here? So about 10 in-house, and then we have about another 8 or 10 online. So thank you all for joining in. Today's speaker is Seogi Kang, who you guys probably know because he was in BC for quite a while. He did his PhD at UBC and in electromagnetic computational EM, and now he's at Stanford doing projects on again airborne EM and imaging groundwater. And I believe the talk is focused on that too. And so yeah, Francis, did we have any announcement on the BCGS side before we kick this off, or I think we just Francis?
Yeah, I think the only announcements would be a reminder to try and get the internships and scholarships underway. That's kind of more of an internal issue that we need to do as executives. But yeah, apart from that, it's great to have the crowd here. I was going to come downtown, but there's COVID in the house, so I'm here.
There you go. Yeah, I can. Well, yeah. Second, and Sug, you can unmute yourself, my friend, and then fire away whenever you are ready.
All right.
Yeah. Okay. You good?
Yeah, thanks. Thank you very much, Tom, for introducing me and also inviting me to this kickoff. I actually didn't know this is the first BCGS meeting in person, so I'm really excited to share my work in California. And today I'm going to talk about time-lapse inversion of airborne electromagnetic data for monitoring saltwater intrusion. And I'm going to use the example in the northern Salinas Valley of California. It's like, I'm not sure you've been there, but it's called Monterey Coast, a beautiful place, lots of people living and lots of irrigation. So kind of the saltwater intrusion is a serious problem there. And also kind of airborne electromagnetic survey, it's pretty common in these days, but the time-lapse survey, it's not common, and there are only a few cases. So it's a kind of like a sort of the early stage of implementation, and see if we can actually do these types of measurements and what are sort of the value that we can get out of it. So that's kind of what I'm kind of generally going to talk about. Okay, I think I probably don't need to introduce much, but I did my PhD with Doug and Lindsay and other colleagues sitting over there, which was a great experience. I studied what's called induced polarization effect in EM data. I'm not going to talk about at all, but that's what I studied. And I'm kind of a co-creator of open source software called SIMPAC. And so all of the example that I'm going to show was built in SIMPAC and accessible through the SIMPAC software, not a main branch, but in a research development branch. And so far, and for the past 3 and 4 years, I've been in California working at Stanford, and really specific to groundwater science and management, and trying to advance the electromagnetic imaging technique for kind of addressing those problems. So that's sort of my kind of a general background. And today I'm going to talk about saltwater intrusion. So let's start with the coastal regions. And in coastal regions, there are almost half of the population lives, and 75% of the cities are located. So this is a very important and vibrant region that we need to take care of it. And in that coastal region, groundwater is a major freshwater source. So this is really important. For instance, the Salinas Valley of California that I'm going to work on today, it's about more than 95% of the water supply. So, I mean, that's really important water source for living. And with population growth and climate change, saltwater can migrate toward inland, what's called saltwater intrusion, and it can threaten the freshwater security. So what the population growth will generate is more pumping. So if you pump the water here, it'll increase the saltwater intrusion. Or if the sea level rise with the climate change, again, it'll also increase the saltwater intrusion. So with both, the freshwater security is in danger. So we need some way to monitor this saltwater intrusion in coastal regions. So this is a really important topic. And obviously, as an EM geophysicist, like EM geophysics can play a critical role for imaging this saltwater intrusion in time. So we could monitor in temporal and spatial domain because of the saltwater. It has lots of ion. It's a great conductor that can generate the large EM signal. So this is like a great topic that can be imaged by EM imaging. And there are many, as you know, there are many EM methods. Today I'm going to focus on airborne electromagnetic method. So like this is actually a SkyTEM system, it's used many like places in California. So you inject the current here, time varying current that will generate a magnetic field, and that'll induce the subsurface. And depending upon the resistivity contrast in the subsurface, we'll measure the secondary signal at the receiver location here, actually here, sorry. I think that's where the magnetic sensor is located. Anyway, so that's the kind of system. An obvious benefit of the system is the speed. We can rapidly map out a large area. Typical speed is about 100 km/h. So if you are using roughly about 4 to 5 kilometer line spacing, you could map out the size of the water basin, which is about like 60 by 60-ish kilometer in a couple of days. So it's a very cost-effective method compared to like the drilling method if you are like drilling. And like what is nice, it's really sensitive to salinity distribution because it's a great conductor. And the downside, like what it provides an indirect information, which is an electrical resistivity. So it is really critical to understand the relationship between electrical resistivity and hydrogeologic structure or hydrogeologic unit that you're trying to image. And the resolution, again, like it's a bit of downside because our resolution, it's degrading with depths as you go deeper because of the diffusive nature of the physics. Okay, so that's the important things to remember. And electrical resistivity, as I said, it's important to understand the relationship between resistivity and hydrogeology. So in the context of salt water, so we're starting from this lower end of the resistivity. So I'm gonna use the consistent color scale. Red is the low resistivity conductor, and the blue is the large resistivity, like a resistor. Starting from the lower end, we have the salt water. Again, lots of ion, it's a great conductor. And as you go toward like a little bit resistive end, we're coming with the sediments. Most of the Californian aquifer system is the sedimentary basin. So it's all like unconsolidated sediments like sand and gravel and clays. So those sediments are set, if they are saturated with salt and freshwater, they could have a little bit higher resistivity than salt water. And then if the sediments are saturated with fresh water, they could have higher resistivity, about 20 to 50 ohm meter, and unsaturated sediments, it has a greater resistivity. So that's sort of the general idea, but obviously there are many other factors that can come into the resistivity. And as you know, like you pick a point here, it's pretty hard to distinguish like what is the different sediments versus like because of the contamination of the salinity coming into the system. So that's the general challenges that we're up against. Even if we can get the resistivity model, it's still pretty hard to distinguish what it is. But yet, like at least we could have some good sensitivity about the salt water and the very low resistivity end. Okay. And I kind of want to start with a little bit of like an empirical or like equation that this like explaining what's the impact of salinity in resistivity form. So I'm going to use the Waxman-Smith's equation, which takes account kind of the clay parts. And here rho is the resistivity and rho inverse is the conductivity. So I'm going to interchangeably use resistivity and conductivity. And T1 means time at one, like at a single time, because we are dealing with the time-lapse. So that's the notation that I'm using. F is the formation factor, which if you're not familiar with it, it's like it's a function of porosity and what's called cementation factor. And TDS is the total dissolved solid. So you can think that this is basically the representation of the salinity, okay? And then K is a constant. And QV and B is the constants related to the clay, amount of clays. So that's the general equation. And then if you kind of put that into a difference form, because we want to see the changes in conductivity or resistivity at two different times or multiple times. If we take the difference, And that if you rearrange this equation that looks like this, and then you can have this form. So this kind of parts related to clays, it's canceled out. So if you actually know the formation factor and the constant K, you can actually directly estimate the TDS, what's changes in TDS from the conductivity, and there's a linear relationship, which is a nice property. And K is relatively easy to estimate. F is pretty hard because it's varying in space a lot. So the technique that we're using is an inversion technique. So we measure the data. Your data, we're measuring like about 50 time channels at a point. So if you're covering a large rate, like a region, we're going to about 50 maps that you can see, but like it could be useful, but not necessarily kind of showing you what is the subsurface structure, resistivity structure look like. So we use a technique called inversion and then obtain a resistivity model that can fit the data. So you could have a one model, but typical problem or challenge that we're up against, there are many resistivity models that can fit the measured data. So that's the general problem that we're up against when we're dealing with just electrical imaging or any types of geophysical imaging problem. And then if we think about a little bit more about the time-lapse approach, so if you do a separate inversion and then subtract to calculate the delta sigma, which is the changes in conductivity, and the error in the inversion or uncertainty inversion can propagate. So it could show changes in salinity, but also could create salinity artifacts. So kind of my overarching research question is like, how do we obtain a reliable estimate of changes in electrical conductivity from time-lapse Airborne EM data? Because like that could generate many different artifacts. Is there a way that we can minimize that artifacts and then have some kind of like changes that we have like relatively high confidence? That's what I want to accomplish. And so let's start with the kind of typical or conventional approach. So if you think about the separate inversion with L2 norm, so L2 norm is the typical form of inversion that we're using. So we're minimizing this objective function, which is a summation of data misfit plus a regularization term. Beta is a trade-off parameter, like kind of providing a relative importance of which one is more important, like your data fit or your prior information and regularization function. And typical regularization that we're using is it's basically a smoothness term. So we're asking when we're inverting it, we're asking, we want resistivity values to be smooth in lateral dimension and the vertical dimension. And that's the typical form of the technique used for airborne EM data, what's called like a spatially or laterally constrained inversion developed by Seogi et al. In 2011. And as I mentioned in the beginning of the talk, time-lapse airborne EM survey is not common at all. So I think the only case that I know is the Brook Punong in Australia. And then this was also related to salinity issues in some of the inland like irrigation setup. But there are like a few. So that's something too important. But for the context of time-lapse airborne inversion, what the time-lapse inversion means, you add a constraint in time dimension as well, because like this was only in the space dimension. So you ask the same kind of question of, in time, we want that resistivity changes in time is somewhat smooth. So you can actually minimize that difference. So that's what's called typical time-lapse inversion. And this, like there was no example for time-lapse airborne EM inversion, but it is quite common in other resistivity inversion like in ERT. There are quite a few other studies done for ERT case. And like rather than kind of assuming L2, we can actually expand that assumption to P norms, which was like work from Fournier. Dom is over there, just the author of this paper. And what I'm doing, I'm expanding that kind of P norm to a time dimension. So that's kind of what I'm sort of like the novelty that I'm bringing in to this community. So what I did, I transferred this mixed LP norm approach to the time dimension. And there's a little bit of kind of understanding what the spatial constraint with LP norm provides us. So if you just use the PR, R means the lateral, like a radial direction. And that's the distribution that you would get. And that's really smooth. And it could also generate a bit of like an artifacts like this. Okay. And then if you, as you decrease the p-value to 1, and you got a little bit sharper transition from red to yellow, and you're kind of eliminating some of the artifacts. And if you set really a small value like 0 value, you almost get really kind of a jump. Okay, so what it could do, it could impose like abrupt changes in resistivity, and it can also clean up unnecessary features that are not needed to fit the data. Okay. So the way it does, like, because we're minimizing this like a gradient, spatial gradient, and then by setting the p equal to 0, we're promoting very sparse distribution in the gradient space. So that's like sort of the kind of underlying mathematics that why we could obtain this types of model by setting different p values. And how about the time dimension? So suppose like we have like an ocean here, and that's the intruded saltwater, and that's the freshwater, and that's the aquifer system. Okay, and that's at time t1. And at time t2, it'll move towards the inland, and then this point will be saturated with the saline water. And if I plot it up like this process, it will look like that. Right? Natural physics is somewhat smooth, like change. Okay, and so if you have many time samples like this is sort of what you're expecting, I guess, with the physics. But what we're measuring is only 2 points. It's a thing at the scale of like airborne geophysics, like we wouldn't do many of this time sampling. It'll be way too much expensive. So we only have few temporal sampling. In such a case, like if this was the case, putting like thinking about using the 2 norm for time constraint is kind of making sense. But if you only have 2 like time sampling in a large amount of time, like thinking about a very abrupt change, it's much more making sense. So you could also use this p norm in time dimension and setting the small p value like 0. So that was kind of the general idea that I am putting to invert the time-lapse Airborne data. And as I said, I'm going to use the field example in northern Salinas Valley of California. And so in a larger picture, this is the Pacific Ocean. That's the California. I'm not sure, BC is not shown, so BC is way over up there. And I am actually about here, I think. That's the Bay Area. And Stanford's like located somewhere here. And that's the Central Valley, which is one of the most productive farmland in the world. They're using lots of groundwater. So there are lots of groundwater issues happening. And that's sort of where my research focus is. And that's the Sierra Nevada mountain ranges. So a lot of snow water coming into the Central Valley and provides the water resources. And Salinas Valley, that's the location that I'm interested in, and especially this Monterey area. This is the study area that I'm interested in. And I wouldn't go too much detail, but the groundwater is the major freshwater supply in the study area. And it is a very productive agricultural sector, meaning they're pumping lots of groundwater that could cause like a saltwater intrusion. And California is suffering from the recent droughts that can really increase the water demand, increasing the pumping. And like, again, saltwater intrusion is a very important local groundwater management problem. And here's our Salinas Valley. I'm zooming into about 20 by 30 kilometer area. And that's what's called Salinas River. And this is the mountain ranges. And that's the valley where the aquifer system is located. And that's the Monterey Bay. And if you like draw a line here and then pull out the hydrogeologic section, that's how it looks like. So it's going north. And basically, there are like 5-layer structures, unconfined aquifer, and there's an aquitard. Aquitard is like a clay, so it's a barrier of the flow. So if you have a big aquitard, that generates a confined aquifer system. So that's unconfined, that's confined, meaning like it's much more pressurized system. And there's two major aquifers, 180 foot aquifer and 400 foot aquifer, and both of them are confined aquifer system. And this is a sedimentary aquifer system composed of coarse grain, sand and gravel, and fine grain clays. And yeah, so 180 feet and 400 foot is the 2 major aquifer, and then that supplies irrigation and municipal water. And if you look at this contours, so that blue sort of region shows like that boundary of the blue region shows a 900 milligram per liter TDS contour from in situ measurements at 180 feet aquifer. You can see the extent of the saltwater intrusion at this aquifer at 180 foot. And if you go deeper at 400 feet aquifer, it's a little bit less, and there's some sort of like isolated salt plume, and that's the level of saltwater intrusion, but it's about like 10 to 20 kilometers into the land, so that could cause a lot of interesting, well, not interesting, but serious problems. And here's our time-lapse airborne EM data. So there was like a 2 airborne EM survey have flown in 2017 May and 2019 April. So it was about the same time in an uncertainty of a couple of weeks. And the first survey, they used the SkyTem 304 system. That's the black dots. That's the data that they were able to acquire, and there was about 650 line kilometer, which is not a big survey, but like significant enough. And I think the line spacing was about 400 to 500 meters, so it was relatively fine, kind of finer resolution airborne survey. And 2019 data is a little bit better coverage. So if you look at the red points, that's the coverage of the 2019 data. And it used the SkyTem 312 system, which was about 900 line kilometer. So 304 and 312 is somewhat, it's pretty similar, but 312 has a little bit deeper, like has a little bit larger moment than 304. I think they wanted to see deeper below that, like intruded salt water. That was sort of the reason why they used a different system. And between these two times, what I'm plotting up is what's called drought index. It's a mix of precipitation and a whole bunch of other inputs related to water, and kind of shows how much kind of drought impact that we had in California. In between 2017 and 19, there was like relatively big drought. So with the drought, what that means, like there will be more pumping in inland that'll cause more saltwater intrusion. So we're expecting that between this time, we're expecting increased saltwater intrusion due to the increased water demand. So that's kind of the somewhat hydrological expectation that we have. And well, like there are some researchers who have worked on the 2017 airborne EM data. So this was my colleague Ian Gottschalk, who worked on 2017 airborne EM data. So this red dot shows the monitoring wells that you actually measure both total dissolved solid, resistivity, so that you can have some sort of co-located information that could give us information like a relationship between resistivity and salinity. And that's the histogram that he was able to make. So like this red region is basically saltwater saturated. So it's about 1 to 3 ohm. And this is freshwater saturated, 20 ohm to 8 ohm. And then undetermined, like this shows kind of the challenges between 3 to 20. It's pretty hard to say whether that's like it's pretty almost impossible to distinguish different sediments. Or salinity. So that was the kind of general challenges, but it kind of gives us a good ballpark what resistivity corresponds to a salinity or freshwater, a saline water or freshwater. And they used the laterally constrained inversion. And this is the result that they've got. Like that's the sort of the three-dimensional view of the resistivity model. So what's this laterally constrained inversion? It's nothing but it's like a stitched inversion. You invert a model in 1D vertical profile, but when you're inverting all of them together and then put a lateral constraint like this using L2 norm. So that's what he did. And if you think about, okay, now I have another data set in a different time, and I want to put this time constraint. And the challenge is using the exact sort of the framework is the location of 2019 data, the sounding location, it's not necessarily exact. So it's actually not intuitive to put a time constraint because the spatial location is slightly different. And so what it means, I had to define a resistivity model in some sort of like a common 3D grid that I can apply the time-lapse inversion. So if I had used the full 3D inversion, I didn't have to worry about this. But still, I think running through the inversion in that scale is pretty expensive. And I mean, there are technical codes that could do it, but still there are a lot of issues to running that 3D inversion at that scale. So I didn't go that route. So what I did, using basically the same 1D types of code, I kind of generated an averaging function. So think about, okay, here's the 3D grid of the resistivity that you're starting, the regular grid. And then you set up an averaging function that can generate vertical profiles of resistivity that you can run a forward modeling that's used for inversion. And that's and then here I was taking into account, like trying to take account the increasing footprint of the EM data with depth. So I used like a typical smoke ring and then this 30-degree angle to estimate the volume representation. And I designed this averaging function that you can start from 3D resistivity and then generate the resistivity at AEM grid. Okay, and then but when I'm inverting for the AEM data, I seek for this 3D grid of resistivity that can fit the 1D data. So I can still use the 1D simulation code, but I'm inverting in 3D. And that kind of sort of addresses the problem of putting the time constraint. So that was the major reason why I did it. And so if I do the separate L2 norm inversion and then plot it up in a three-dimensional view, I'm just plotting some sort of cutoff value of the 3D resistivity model in 2017. And that's the Monterey Bay. And this is about 20 kilometer by 23 kilometer scale. So the south to north and the west to east. Again, that's the ocean side. And you can clearly see this is into the saltwater. So I cutoff value was about 5 meter, and this is the sort of freshwater or unsaturated part of the subsurface that could be imaged from Airborne data. So even using the conventional technique, you could actually got pretty kind of cool image, and then providing sort of large scale information about the subsurface salinity distribution. And like if I plot it up at 50 to 60 meter below the sea level, and that was the sort of the center part of the 180-foot aquifer, one of the, which was the location we got the sort of the strongest like saltwater intrusion. And that's the 2017 resistivity model at this interval. And I'm plotting up the 5 meter contour as kind of a landmark. And then this red region shows like kind of intruded salt water. And I also got like a 2019 resistivity model. They are at the same grid, so you can take the difference and a form of conductivity. And that's how it looks like. So the blue is the kind of negative conductivity, meaning getting fresher. And the red means positive conductivity, getting more saline. Okay, that's how it looks like. So it seems like there are lots of changes happening if you simply calculate, do a separate inversion and calculate the difference. But like the question is, are they really like the change? Like are those changes really happening in the subsurface, or simply there are the artifacts of the inversion? So those are sort of the kind of motivating question that I had. And if I put the time constraint with L2, and that's how it looks like. So you can actually remove quite a bit of like a kind of conductivity changes and have this information. You can kind of like, now you're starting to see some of this increasing salinity or like increasing conductivity at the edge of this contour line, which we're sort of expecting to see the changes. So even putting the L2, like we could do quite a bit of like, we could kind of remove some of the artifacts. And how about the impact of L0 norm? So we like I kind of explained why I've chosen L0, because like it could, in space and time, it could remove some of the spatial artifacts. And then given we have only have 2 temporal sampling, it makes sense to put an L0 time constraint for the time as well. So this is the same kind of plan view of the 2017 resistivity model at a 180-foot aquifer. And I picked the same 5 meter. So if you actually compare that with the L2, so you see kind of the same sort of feature that I have kind of explained. So you see like this, for instance, is kind of gone here. So we're sort of penalizing unnecessary structure and also putting a sharp contrast in between here and there. And this is the 2019 resistivity. It's hard to see the change in this form, but if you look at here and there, it's changing. And if you look at there, And there it is changing. If I calculate the conductivity difference, it's getting more clear. And compared to the L2 case, we removed a lot of like kind of structures. So that those kind of differences were not necessarily needed to fit the data. So that means like for those kind of structures that we're seeing here, we have a little bit higher, we have a bit higher confidence about what's changing in the subsurface. So that's so kind of we address those research question posed. And so, but like, so as a geophysicist, that's cool, and I got sort of what I expected. So I could write up a paper and done. But what? So what? Like, what does it matter for like hydrology and this groundwater issues in the Salinas Valley? So that's kind of what I'm sort of interested in to address for this part. And so let's start with the resistivity model, the best resistivity model from this LP or L0 norm inversion, in L0 norm time-lapse inversion. This is a 2017 at 180 feet aquifer. And again, this is the 5 ohm meter contour. And if you think about the 5 ohm meter, that was like this 3 ohm meter is about like 10,000 milligram per liter, if you roughly match it. So it's kind of closer to like a 10,000 milligram per liter as opposed to 900 milligram per liter that the this like local water agency used to map out the extent of intruded salt water. So, and this was used for like this was from in situ monitoring wells. Okay, so it makes sense because like this is much sort of higher salinity front compared to this. Okay, but what's actually really interesting as like there are many monitoring wells, but once this front of this 900 milligram per liter past the monitoring wells, they stop monitoring the data. They stop measuring the data. So they don't really have a measurement for like high salinity information. So like in the context of water quality, I think it may not matter, but sometimes if you actually think about like putting the fresh water to sort of like neutralize the saline water, and sometimes they want to make a barrier of the fresh water to kind of oppose this saltwater intrusion. In such a case, actually, you want to know where is the high saline zones. So I think what AEM provide is somewhat kind of compensating information that is lacking in the in situ monitoring well data. Anyway, so that's kind of interesting information. And so if you move on to the conductivity difference, so what we're calculating is the difference between 2019 and 17 conductivity. And given there was a drop between 2 times, we're expecting increase in salinity. So what I did, I just put a positive projection. So I'm just gonna filter out all the negative values and then plotted up the positive value, which shows the increase in salinity. And as I said, if we know the K value and F value, we can transform the delta sigma conductivity difference to a TDS value. So that's what I did. So I just generate a map that kind of converts the conductivity difference to a TDS. And F value, I used the literature value, like from that Goschalk et al. They estimated from in situ monitoring well data. And the K was also measured and calibrated from those in situ well data. So you can actually, now you have, let's say this red color is about 0.1, you can actually have an idea what is the TDS value, changes in TDS value that was about 4,000 milligram per liter, which is a huge salinity change that we're seeing. And those are, I'm pointing out 3 major locations that we're seeing large conductivity difference. And I think that those are sort of the locations where saltwater is like intruding quite a bit. Even between 2017 and 19, which is pretty short time span for like when you're thinking about the saltwater intrusion process, because it's much like the process is happening in a much longer time span. And so the question is like, okay, we're seeing this as a geophysicist, we're relatively confident those changes is real. And can we compare with other data? So that's what I'm going to compare. What I'm going to show is the sort of time transition of that the like 900 milligram per contour in like every 10 years. Okay. So for instance, like this starting from 1965, and that was what they mapped for 900 milligram per contour. And the red one is between 1965 and 1975. So I'm trying to pick up roughly 10-year time span and showing how much saltwater intrusion is happening and where that trend, like a saltwater intrusion is happening. What does the shape look like? So this is 2075 to 85, 85 to 97. So I'm going to show one more time. But just kind of see the shapes and how they correlate with the point, like the arrows that I have pointed out. So I think those are sort of the typical location where this large amount of saltwater intrusion is happening. But I think what we're seeing is very high kind of salinity with like a high salinity front. So that's at least making sense, and the spatial patterns of the final conductivity difference show similarity with temporal changes in TDS contours. So that was actually good news, good kind of spatial features to see. So to conclude, we developed a time-lapse airborne inversion methodology using LP norm, spatial and time constraints. And we found that the airborne EM method is sensitive to the changes in high salinity zones, about 10,000 milligram per liter. So and delineate the saltwater intrusion front with the high salinity and identify changes in salinity around the front. But what that means, if you really want to image the low sort of salinity infiltration front, like 900 milligram per liter, airborne EM is not enough. So that was sort of the limitation. But I think airborne EM method provides an effective way to monitor large-scale salinity changes in zones with high salinity, which sometimes can be very important depending upon the purpose of the activities related to saltwater intrusion. And I think it can be useful in situation when monitoring wells are opposite. So if you don't have monitoring wells, this is the only information that you can get about the salinity distribution. And if you're thinking about you want to monitor a saltwater mediation process, if you want to inject the water or pump the salt water so that you can remove those saltwater or brackish water, this is a great tool because you may want to know where the high saline zones are, and then also want to monitor how effective your kind of remediation activities is. And as I said, it's limited, because the major purpose, thing in terms of monitoring, they want to see those low infiltration front because it kind of divides either that's drinkable water or not drinkable water, or usable for irrigation or not. But I think there's, as I said, there's some benefit. But if just the airborne EM data were used, absolutely there are some limitation, and it's important to recognize. But yet there's a possibility exists, I think, by integrating this airborne data with in situ data, or integrating airborne EM data with a saltwater intrusion model, more like a groundwater physics-based model. We could improve the entire model so that we can have better capability to monitor saltwater intrusion in this region. And by doing so, I think we can maximize the value of this time-lapse airborne EM data for monitoring saltwater intrusion. What I have kind of provided is sort of the start of the going toward this goal. I think that's useful. And I think here's a little bit of more outlook about where we're going. Obviously, it's not just California. There's overall emerging use of airborne EM method or data for groundwater application. So this is an example in a statewide airborne EM survey in California. This is a regional survey basically covering entire Central Valley, and with about 4 to 12 kilometer line spacing. They finished actually mapping the Central Valley, and data will be completely available to anyone who wants to use the data. And that means there's a large, also there's a large potential to conduct even more EM surveys, because it's a pretty large line spacing. If you want to find a resolution resistivity image, they would fly again or do a ground-based EM survey. And that's actually what's happening in California. So that's exciting. And this is kind of like an image that you can get out of it from those statewide airborne EM survey. And this is really kind of super standing. And that's what's called Tulare Lake. It's dry lake now, but it's there used to be there used to be a lake, and there are lots of clays. And I think we're interpreting that as containing lots of salt in the clays because of the origin of the clays. And that's sort of the level that we're saying. And another survey, that's is what we've done. in our environmental geophysics group, we were looking for what's called paleo valley or incised valley fill, which could be used as a recharge because like we're curious about whether there's like really coarse-grained valley fill starting from the foothill coming into the valley, such that you can, if you pour the water at the foothill, if that water pulse can go into the valley and recharge the aquifer, that would be great. So we were able to find those big scale structure. So anyway, there are lots of interesting things happening in the context of the survey. But the really question is like, okay, we got this amazing data set. Are we really kind of maximizing the value? And an obvious transition is like, kind of, can we use this amazing geophysical data to constrain the hydrologic process with EM data? And that's sort of where we're going. So I'm kind of working with the engineering firm related to that, the Airborne EM data. That was the original project that why I started that project. And we want to combine this time-lapse Airborne EM data, well data, into saltwater intrusion model that can update their model. And this is an interesting diagram. So what I'm plotting up is their calibrated saltwater intrusion model, but that means they tried to fit the in situ measurement by kind of changing some of the parameters in the saltwater intrusion modeling. And if I plot it up the 5,000 milligram per contour in this 180-foot aquifer, that's how it looks like. And if I pick up the 5 meter contour from Airborne EM, that final survey from our time-lapse inversion, this looks like this. So, I mean, neither of them are right, but this difference shows the gap, meaning the potential to improve the saltwater intrusion model by intuiting the Airborne data into the process. Obviously, very challenging process, but we're kind of working on it and helping to make some progress. And that was it. So I thank to a bunch of people, and especially for SIMPIC community and other people from our environmental geophysics group. Thank you very much.
Thank you, Seogi. The in-person audience is excited. Thanks, Seogi. It was a perfect balance of theoretical and applied geophysics. It was really, really well done. Always a fan of your great presentations. So yeah, let's open the floor to questions. Other people here are online. Just unmute yourself and fire off questions for Seogi. Maybe I'll start one then. So can you elaborate, Sag, on what's in the temporal term for the reg? Is it like a subtraction or what's in there?
Can you say the question again?
Yeah. What is in the temporal function? Like, are you just subtracting time 1 versus time 2? What's in it? What are you?
Yes.
Yeah.
Yes. It's simply like a difference between T1 and T2, and then using a P norm of that difference.
Great.
Yeah,
go for it, Lindsay.
Sure. I'll jump into the question, Seogi. Can you hear me okay?
Yep.
Okay. Your averaging function is really a cool approach with the smoke rings. But near the surface, I could imagine, we have a small footprint. And so in the inversion, are you using like a smoothing across places, or like what do you expect anything strange to happen when you've got a small footprint near the surface?
Yeah, great question. And so there were a little bit of pre-processing needed. So when I had to select some points. So once you got a grid, and then within the grid, you can get many points. Like I was using about 150 meter by 150 meter cells, uniform cells. So within the grid, I'm going to have many points. Like I could have some points. So I had to select a point, and I used very simple metric, like this closest point to the center. But I could have come up with a better way to sample which one is the best representation of a cell, but I didn't go that far. And you're right, even for 150 meter, so that the radius is about 20 meter. So it's so I had to put some sort of the minimum value, which is the cell size. So at the top, at least I'm picking up one cell.
Thanks, Seogi. Seogi, can you put the final map that you had for the change in conductivity? It was all really concentrated.
Yep. This one, is that?
Yeah. So that's a really interesting thing that comes back again.
Huh.
We lost you, so yeah.
Yeah, I'll just do,
Yeah, that's okay like that. Yeah, it's still.
yeah, okay. I think I'll just work with this, sorry.
Okay, so now you've got these really large changes in conductivity that are kind of spatially defined. So first of all, are those changes, are they all at that 180-foot aquifer?
Mostly. I think there are some in the near surface, like at the very near surface, but that part I'm not sure whether that's really changing, because like at the near surface, we're not expecting much changes other than the water table.
So these changes that you see are sort of integrated vertical changes or over a whole column, I think.
Well, it's only like few cells. It's 50. I think it was only a 10-meter interval. Just give me a sec. Yeah, it was 50 to 60 meters. So it's integrated over, I think I used a 5-meter. So it's only 2 cells. So it's integrated over 2 cells.
But it's located at that 180-foot aquifer.
Yes, it's pretty like a layered system. So there's a little bit of up and down of the top of the 180 feet aquifer, but that like the 50 to 60 meter interval is throughout that the layering of the
Okay,
foot aquifer.
and then, I mean, have there been wells drilled into there that could have been used for monitoring so you could actually see what happened?
Yeah, that's what I was hoping. And again, as I said, once the monitoring like this, the contour is past a point, they stop monitoring. So like at this point, they're not monitoring anymore. So they only had like so kind of, we don't really have that data for high salinity information. So it was pretty hard to find any ground truthing, like see like can I see the match between the monitoring wells and the conductivity changes.
So are these monitoring wells expensive to maintain? And once they've got a monitoring well, why don't they keep monitoring?
That's a great question, and I don't have a great answer. I'm not sure why, like it's probably there, and why they cannot keep monitoring. I don't know.
Anyway, thanks, Seogi. That was really nice result.
You, Doug?
Seogi, Dennis Woods here. Can I ask you some geological questions? Actually, I'm a little bit
I'll try my best.
and I'm specifically thinking of other places. How typical is this result of the saltwater intrusion of the roughly 10 kilometers into the ocean? Is this something that's seen all over the world, or?
That's a great question, and I think I don't have a great answer. And I think if the very productive irrigation area is close by coastal region, I guess like it could always happen. So the Salinas Valley, they're like very productive irrigation area. And then with the droughts, so I think it's a combination of irrigation area and the droughts. So if there's any region kind of satisfying those 2 conditions like droughts and irrigation, I'm pretty sure, and then use of groundwater, I'm pretty sure like you see many other regions like this. So I think this is not the only region, I think.
Yeah, I'm getting way beyond your geophysics expertise in this, and really this questions are more for geomorphologists. But we've got a project in West Greenland where I think we are seeing saltwater intrusion up glacial valleys, U-shaped valleys that terminate in the ocean. And we're thinking we're seeing 5-10 kilometers inland. The bottom of the valleys would be a lot of sediment. But there's no irrigation, nothing going on. It's just a natural environment.
Right, and then I mean, if the salt, like so, as I said, there are two things, right? Sea level rise and the pumping. So if the sea level is rising over there, I mean, you could obviously get more saltwater intrusion. So it's not like like if either one is satisfied, I think you could see some saltwater intrusion. This was almost like I mean, I'm pretty sure it's an extreme sort of case, but I think the level of saltwater intrusion, I think you could see in many places, I guess.
So Dennis, was that inferred from the geophysical measurement?
Airborne.
So you're like 5 or 10 kilometers from the coast.
We're seeing a surprising amount of response. It's surprised to know. It's not a world. It's widespread in the valleys.
Yeah, and I'm not sure this helps, but sometimes
Well,
there's
easiest excuse is that we've got saltwater intrusion, but I'm not sure it's true. This is what I've been telling the client, but I'm not entirely sure.
right. Yeah, I'm not sure that's relevant, but if you go to a little bit like east to the Sierras, there's what's called Indian Wells Valley. This is the closed basin. So there's no outlet of water. So it's surrounded by mountains. And then if the water is kept running off and then percolating to the ground, it could actually generate like what's called playa deposit. So it could accumulate a lot of salts. And then over a long time period, it could accumulate and ever, and then it could generate the big salinity plume. So that's what we were able to see in those like closed basin called Indian Wells Valley, and like it's a pretty large plume, like tens of kilometers plume, but maybe not really relevant for your case history, but
That sounds
it's also possible.
I'm gonna look into that a little bit.
Francis? Go for it.
Yeah, hi, can you hear me?
Yeah.
Awesome. Thanks, Seogi. This is great. A couple of your figures, as well as Dennis's comment, lead me to wonder whether you have colleagues who can do the hydrology for those sites. The sort of thing you'd like to be able to do is try to model flow within those aquifers based on drawdown from wells that are being pulled. So can you generate heads which are going to generate sucking, which pulls the salt water in? And in the Greenland context, you're going to have to somehow generate appropriate differences in head in order to actually drive salt water uphill. And these, I mean, I'm not a hydrogeologist, but these are pretty sort of standard modeling exercises that the hydrogeologists could do. I mean, in our department, we would ask Roger or Ali to do this in their early courses. So I guess the question is, do you have colleagues who do that sort of work to help understand the hydrogeology of the situation?
Yes. So the time-lapse inversion is not the goal of the project that I am working on. So what we actually are doing, like so this guys from engineering firms, they're supporting the county by generating the saltwater intrusion model. And this was a research project that we are integrating this Airborne data to update the saltwater intrusion model. And this is the result of the salinity distribution from their calibrated model. So obviously we have had as well as the salinity distribution, but we're trying to update some of the modeling parameters like hydraulic conductivity distribution or the boundary conditions of this model, such that like, we can fit both airborne data as well as the in situ measurement. That's sort of where we're going now.
Yeah, I guess what would be, what I can imagine is the constraints that the inversion work can generate can perhaps be can serve as constraints on the hydrogeologists' work, which, I mean, we're sort of talking about the difference between the geophysics and the information that provides, and the question at hand, which is what's the hazard we're dealing with? How quickly will the Salinas Valley become end up with an aquifer that they can't use? And so that's a hydrogeology question. And I think to me the interesting part is how the geophysics contributes to what the hydrologists are modeling.
Yes, that's the ideal scenario. So we're hoping to generate a technique that could do it. And actually, the county is planning to do another time-lapse survey, not in a in the near future, but at some point. And so they want to actually use that as an integral tool of monitoring that they're like saltwater intrusion. And because this is very productive and there are they have lots of money, I guess. So, I mean, although this is an expensive survey, I think in the context, given the importance of the problem, they are willing to pay about that money to do the monitoring. So on our end, we actually need to develop a quality sort of workflow that could integrate all the information possible to have some monitoring capability.
Yeah, I think we have time for one more quick question, if anyone else. Yeah.
Sorry. So yeah, heard you mention that when you measure the data for like in 2019, then the error will not correctly apply to the deposition to measure the data, right? So how does this uncertainty affect your model, and then how do you deal with this uncertainty?
It's hard to hear, Mimi. Can you
I mean, you
ask again?
Error, right? So, for example, in the time-lapse data that you measure, like after several years, the the airplane cannot fly to the exactly same location to measure the data, right?
It's not at the well. They tried their best to fly over, but it's not exact because it's pretty hard.
Yeah. So this
To
is
fly over.
uncertainty, right?
It's not uncertainty, but there was the motivation to build this averaging function, because if they are not at the same location, it's hard to put a time constraint on it. So there was sort of the motivation on my end to generate an averaging function that you could have work with the same 3D grid, but still use the 1D like for modeling.
Would it affect your result a lot?
What was your comment, Mimi?
How much would it affect your the output, the final models? So having
Good question. I don't know, because I haven't tried, I was not able to try, because even if you apply, then you may need to interpolate and subtract. I haven't tried that, so I'm not sure how much impact that would have made. Yeah, but I think probably similar to like if you do the separate inversion, interpolate into 3D grid and generate the map, you would likely get the similar sort of image that I have shown for the separate L2 norm case. That would be my expectation. Because error propagates through the interpolation as well. So yeah, that's be my expectation, but I'm not sure because I haven't tried.
Like it kind of seems like your time-dependent regularization term is doing a lot of work in that kind of way.
It is. It is.
And I guess I was wondering how you chose the alphas for that, the relative weighting and how much.
Right. Great question. And I think there are a lot of, actually, I didn't know, but there are a lot of papers talking about that. And what I have used very simple metric. I used the same amount of constraint that I gave to the spatial, like a lateral constraint. So it was almost equal importance. And then that seemed to me reasonable enough because I mean, you could come up with all this optimized value and then or a whole bunch of other complicated strategy. But at the end, I think it's all like it probably really depends upon the case by case. So I thought starting with the simple is better. And then at least for this case study, it was pretty effective. So I was happy.
So rather than trying to do a time-lapse EM in the air, trying to put down the exact same path, and rather than trying to keep boreholes going all the time, why not set up a bunch of stations, ground stations, in some convenient locations, and half a dozen or so.
Yeah, I think that
after year.
right.
Exactly.
Right. I think there, yeah, that absolutely opens up the possibility, because I think in the context of like seeing the salt water, you may not need that much inline spacing of airborne data. And like having some, like, I don't know, like dozens of EM stations along the coast, like along the area that you think things are changing, that could be quite effective. But yeah, to be honest, I'm not in the position that I could suggest those kind of things. But yeah, if I have a chance, I would. But it's a great idea, though.
Great. Well, let's thank again Sug for his time. And, a round of applause.
Thank you so much.
All right. Well, thanks again, everyone. And I guess we'll send a newsletter soon for our next talk in October, I believe. Hopefully, we have a speaker in October. Okay. Bye-bye.